I'm Antonio Sale, and in this video we are going to discuss control strategies when we have an excess of manipulated variables, of actuators that can modify, let's say, a single control variable, but we have two manipulated ones. This will be the first video that we will devote to this issue. Let us first start by motivating which kind of applications we may have requiring this setup. We may have a heat exchanger with a bypass valve, so both the steam supply valve and the bypass valve have an effect on the outlet temperature. We may have a tank in which we have steam heat exchanger and a resistor with some need of coordination between them. Maybe we have a fan and coil in order to lower the temperature of a fluid, and a heat exchanger with steam supply to increase that temperature. We may have a mixer in which we have a heat exchanger in each of the inflows. Or we may have a complex setup in which, well, for instance, we wish to neutralize a base and we have two acid controlled inflows, so that also in theory we could perfectly neutralize with acid 1 everything, as sensors are not accurate. Purity and input pH may be also varying, etc. We may decide to do it in a couple of stages. First stage with acid 1 and the second stage with acid 2. Or, in order to control the outlet water temperature, we can use either the heating element in tank 2 in here or the steam supply in this heat exchanger. So in all these situations we have one control variable, be it pH, temperature and the like, but we have several manipulated variables that act upon it, and we wish a control structure taking advantage of the extra control capabilities we have due to the fact of the excess manipulated variable. So in this video we will put forward some strategies and discuss their applicability and interrelations. And we will divide our account on all this stuff in two broad categories. A first one in which I label it as just one active control, let's say, so that there is only one temperature controller, let's say, that decides a single temperature correction control action, and then it's split or shared among the available actuators. Or, well, the other option will be introducing extra set points, extra controlled variables, and use, let's say, additional control loops, which are all of them active at the same time. These will be gradual and cascade strategies. So in this first video, we will discuss just these ones: load balancing, split range, and override, in which, well, there are two control loops in the override setup, but only one of them is designed to operate in normal situations. So, well, explaining the details on all these strategies is what we are going to do next. Let's go. The first situation we are going to consider is, say, load balancing. So we can imagine a couple of heat exchangers, each of them able to heat one of the inflows to a mixer, and we may wish to control temperature. So we have here a temperature transmitter that sends a sensor reading to a temperature controller. This may be a PID that decides a given control action, and, well, load balancing would be, for instance, sending, if this requires 4 kilowatts of heating power, then sending, let's say, 2 kilowatts each. This situation will be an exactly balanced load. So we share the control effort between the different actuators, either equally or, well, depending on the operating point of the inflows or whatever, we may decide to split it into 2/3, 1/3, or whatever. Then this is load balancing. The thing is that, is this actually a good option? Well, that depends on quite a few things, in the sense that, come on, maybe instead of a 3 kilowatt rated power, let's say, heat transfer, we may consider the option of just building a single 6 kilowatt heat exchanger. So, depending on the price of building this stuff, the available space, maybe this 2 exchanger option is nonsense. So, it depends on those specific details. And also, maybe this thing will be advisable if, let's say, 50-50 share must be better than just one of them operating and the other one being off, if my power requirements are less than 3 kilowatts, let's say. And which is better? Well, it depends on the technology. I mean, in a car with front and rear electric motors, let's say, is it better when we are, cruising to send power equally to front and rear wheels? Or is it better to send most of the power to the front wheels? Well, we need to decide this. And it may be a fixed proportion, or maybe the share of power may depend on the driving conditions, on the car speed, or whatever. So this load balancing may require either a static analysis prior to building this equipment to decide the best way of balancing the load, or maybe it will require real-time optimization. So depending on the temperature set points, on the inflow values, etc., we may decide a different share each time. So even if 50-50 sharing is so the simplest example we may think of, well, this is kind of just a glimpse on what real-time optimization, for instance, deciding the power that a given power station must generate to fulfill global power demand, all those things may require complex real-time optimization. But okay, in simple, temperature control stuff, we are not going to do that. And we will just decide on whether we split 50-50 the heating power command to the cascade servo valve in the steam supply, let's say. Or, the other extreme is, of course, 100%, 0% if I am below 3 kilowatts. And of course, that thing is called split range. If this thing is, for whatever technological reason, worse than this, then we have split range. What do I mean with split range? Well, in this case, if my demand is 4 kilowatts, then I might decide that I will demand top power from one of the exchangers and the remaining bit from the other one. So, a split range would be programming in my PLC or whatever, something that exchanger 1 in pink, exchanger 2 in cyan, like this. If demand is below 3 kilowatts, I just use heat exchanger 1. If demand is between 3 and 6, I use heat exchanger 1 full power and the remaining thing on heat exchanger 2. And well, if demand is above 6 kilowatts, then I cannot supply it. So I will have my combined 2 actuator saturation. So, well, this is the split range setup. And of course, the most famous split range configuration will be a fan just blowing into a coil to refrigerate the fluid and the steam supply in a heat exchanger to heat it. So in that case, depending on my demand, I would activate either the fan for negative demands or the steam for positive demands. Good, but if actuators in split range are heterogeneous, like this one, I mean, in here, if I had two identical heat exchangers, then, it seems easy. But if my actuators are different, then maybe, this steam stuff, 1% opening on my valve hits 1 centigrade, but in here it is 20 revolutions per minute, the thing that cools 1 centigrade. So if I tune my PID, let's say, with the heating gain and time constant, then my end loop will have a split range switch, so that if positive, then it will act on the steam valve, but if negative, then we would need to add a gain correction of 20 to devise the fan RPM set point. So we would need, to have gain corrections, and hopefully also the time constants need to be similar, because otherwise maybe a good PID tuning for heating may be a deficient one for cooling. So in that case, we would also need some kind of gain scheduling that would complicate things. But if my underlying process is dominantly first order, then this would work okay. But if we have very different dynamics in each of the manipulated variables, be it here or whatever, then we may have stability problems or need of retuning, depending on the power ranges or set points or whatever, to accommodate for the difference in time constants. So in summary, if we have a couple of manipulated variables with similar bandwidth, then we can decide to share the control effort if for whatever technological reason that sharing is better than just split range, in which we utilize 100% of one of the variables unless that one saturates and then we need the extra one. For instance, we may use a split range if I can heat some of my process elements with hot water from a solar installation in my roof, and only if I don't have enough heating power from the sun, then I may connect a gas burner or electrical heating from the grid, so that I save money with that recommended split range configuration. And as I said, load balancing versus split range may need real-time optimization on the price of electricity versus gas, or depending on the operating point or whatever. So this is simple until complex applications make it complicated. But okay, the basic idea nevertheless is simple enough to understand. Now, the next strategy we are going to discuss is override, in which, basically we have just one controller in operation, but we have my second manipulated variable just as a backup in case of some failure. So the greatest scheme of things will be like this. I may have a heat exchanger with some steam or hot water coming from my process that is, basically cheap for me to produce, and that control loop in red would be the nominal control loop. And I may also have a resistor here that will be the emergency control loop, and I will activate it just when something strange happens and this water is about to freeze. So I may have a secondary temperature sensor just in case the primary one fails, a secondary temperature controller, and it will get a set point that maybe, it's 4 centigrades, emergency set point, not accessible to the operator unless you put a lot of passwords in it, so that this secondary controller will activate the resistor only when the water temperature drops below 4 centigrades. So a nominal loop will work hopefully every time, and the emergency loop will never activate. But if some failure in the red nominal loop or some extremely unlikely meteorological event such as minus 20 centigrades ambient temperature, then okay, in that case I will connect my safety heating resistor. Then this circumstance is called override. This is a kind of split range in the sense that, okay, when my heating power of this exchanger is not enough, then I activate my resistor, but a normal split range would activate the resistor at the exact same moment this heat exchanger saturates, this valve is fully open. That would be just a normal split range, but the override will activate the resistor only if an emergency situation arises. So if my steam valve is fully open and water is at 10 centigrades, then I will allow for degraded behavior and I will only switch the resistor when that degradation is large enough to be dangerous for the integrity of my process. So in that case, this override is a kind of refinement of the split range with that degraded operation in between saturation of the steam and activation of the resistor. So well, let us summarize and conclude this video. In this video we have described 3 ways of having one controlled variable with 2 actuators, with 2 manipulated variables. We have load balancing or split range. Load balancing would share the effort between similar actuators. Split range will wait until a main actuator, the one with cheap energy, let's say, saturates, and only then it will connect the second auxiliary, more expensive power source. We may need real-time optimization in complex setups. And the third option was the override control, in which it was similar to the split range stuff, let's say, but allowing degraded behavior without connecting the extra power source unless an emergency situation arises, and it is only then when I connect the extra power. Maybe the emergency situation is caused by a failure of the main loop. In this override setup, we must be careful with anti-wind-up stuff and whatever, but that's not the objective of this video. So these are, let's say, the 3 situations in which having one control variable, I just tune one control loop, basically for normal operation. Then next video, we'll discuss gradual and cascade options in which I will have secondary controlled variables, secondary set points to follow, so that I intentionally will need to tune 2 controllers. But we'll leave that for the second video for brevity. So we conclude now the presentation here. Thanks for watching.